Typically, light travels in a straight line, unless we insert some material, then it gets bent. If you want to find out why this happens, stick around and we'll check it out. First of all, let's have a look at what a light wave looks like. Here depicted in purple, you can see a sine shape of the light wave and it's propagating to the right-hand side. Sine means that the peak maximums have a constant distance between each other, and this distance is called the wavelength. Now, if we imagine that this is not only a two-dimensional line, but a three-dimensional surface, then we could flip it by 90 degrees. This means we are taking a look from the top, and those red lines, they are representing the peak maximums. They are called wavefronts. And the direction of propagation, this basically means the light beam, is always perpendicular to this wavefronts. If we now go to the right-hand side, here you can also see a sine-shaped wave, and obviously the wavelength is shorter. One could easily think, oh, this changes also the frequency of the light, which means the color of the light, but this is not always true. Because if light is traveling in different materials, this means materials of different optical density, this can reduce or let's say change the speed of light. In a material with higher optical density, the traveling speed of light is slowed down, and this means that the wavelength is also shorter without changing the frequency. Now, what happens if we now have two materials and there's a surface? Let's have a closer look here. The black line indicates the interface between two materials. One is of lower optical density, the other one of a higher optical density. And once again, here you can see the wavefronts, these horizontal red lines. And the light beam is going perpendicular to this surface. And what we can see is it continues in the second material, while the wavelength is changed. So in this case, the wavelength is getting shorter. It's due to the fact, as discussed before, that the speed of light is slowed down. Now, what happens if the incident beam has an angle and is not perpendicular? Here we have practically the same setup. The incident beam now has an angle, and the point where we have to look up closer is the interface here. We see the wavefront here, and it's pure physics that the wavefront has to go continuously from one material to the other material. And as the wavelength changed in the two materials, the only solution to that is that the beam in the optical denser material is refracted. This means it has a lower angle than the beam in the initial material. Now, what does this mean? Coming back to our experiment from the beginning. Once again, here we have our laser. We have this glass or plastic block. And what you can clearly see is that with a large incoming angle, the beam inside the material is lower. What is interesting to see here is that at the second surface here, or second interface, where we go from the denser material to the lower density material, the effect is reversed. This means the incoming beam and the outgoing beam is completely parallel. I hope you learned something today. If so, please leave a comment and see you in one of the next videos. Bye bye.